Hello, welcome to our ADSA video presentation. Our focus will be mainly on biparental heap or Beep and its other variations. Let me introduce our group members. I am Himanshi Swaroop and my colleague Pankaj Jinslani and my other colleague Maitri Sarma. So, what's Beep? Beep is an implicit dynamic data structure which is similar to a heap, a normal heap. The difference is only that every node will have two parents, and we can implement it with a simple array, which has approximately a square root of 2n blocks. The ith block consists of the I elements stored from position I into I minus 1 by 2 plus 1 through position I into I plus 1 by 2. This enables us to increase or decrease the size of the entire structure while changing the number of elements in only one block. So let's talk about the ordering of this structure. The kth element of the jth block is less than both the kth and the k plus 1th elements of the block j plus 1. So the height of the structure is about square root of 2n. So you can see in the figure here, the height is of order square root of n, and the minimum element is at the top and the bigger elements are at the bottom. So here you can see the example of the Beep with 12 elements stored in an array and this implicit structure. So let's talk about some amazing facts about Beep. So there are about square root of factorial n beeps possible on a set of n elements. And n by 2 into log n comparisons are necessary on average for the creation of beep, which gives the time complexity of order of n log n. The minimum element can be found in the first location, so the extract min operation takes order of constant time. The maximum element is present in the last square root of 2n locations. An insertion method is similar to that of heap. The new element is inserted into location n plus 1 of the array. So like if we have to insert into the structure an element which is smaller than all the elements currently stored, then every element on some parent offspring path from location 1 to one of the last square root of 2n locations must be moved. So about the deletion operation, after determining the location of the element to be removed, move that element at the nth position to its location, and then this element can be moved up or down according to the structure of the beep. So the cost of deletion is order of square root of 2n, which is equivalent to its height. Here, now let's talk about the search operation. For this operation, we need an upper left triangular matrix here, as you can see in the figure. So the steps for searching are, we will start from the leftmost corner of the matrix with this cell, and we'll compare the element with x, and if it is less than the element, then we will move left one position, and if it exceeds with them with x, if x exceeds the element, then we can move left and then down. Otherwise, if the bottom element is present, we can just move down, and if the element is equal to x, then we can stop the search. So let's talk about the rotated list. The main trick employed is to store blocks of elements in an arbitrary cyclic shift of the sorted order. We call such a block a rotated list. Here you can see as in the figure. So let's talk about the basic operations of rotated list. First, finding the minimum. Again, you can find the element in the first array location. Finding the maximum, we can find the maximum in one of the locations in the last blocks, which is in order square root of log 2n. Then search operation. Our basic approach is to perform a simple binary search until it is determined that desired element lies in one of the two consecutive blocks. Again, the array is partitioned into blocks such that the ith block contains I elements, and the ordering is as follows. As all the elements in the block I will be less than or equal to all the elements in the block I plus 1. And the block I is a rotated list of the size I. So here you can see that this second block elements are less than third block elements, and all the blocks I is a rotated list of size I. So we use bisection technique for finding minimum of rotated list containing distinct elements. The procedure is as follows for finding minimum in the interval f to L. If f is equals to L, then obviously the minimum is found at that location. Otherwise, minimum is found at the position average of f plus L. Then element at M, if element at M is less than element at L, then the minimum is in the interval f to M, and we have to apply the procedure recursively. And if the element at M is greater than element at L, then the minimum is in M plus 1 to L interval, and we again have to apply the procedure recursively. It can be shown that this process requires at most log-n comparisons if I is the size of the block. So the limitation of a technique is that if the elements are repeating, then this search procedure for a block may not succeed. So here you can see in the figure, finding the minimum in the rotated list. Now let's talk about something deep with rotated lists. So the ith block is stored from location this through location this. Each block is divided into I consecutive subblocks containing I elements each. The subblock corresponds to the node of the Beep, and each subblock is stored as a rotated list. And the height of the structure is about cube root of 3n, which is equal to the number of blocks. All the elements of the kth subblock of the jth block are less than all the elements of the kth and the k plus 1th subblocks of block j plus 1. So let's talk about facts about Beep with rotated lists. The deletion operation or the insertion operation takes order of cube root of n into log n time. Extract minimum takes constant order of time. And extract max takes cube root of n into log n time. Search takes cube root of n into log n time. Here you can see in the figure how the Beep of a rotated list is shown here with the height of cube root of n. Now let's see the summary of it. Beep, here you can see the search is square root of n, rotated list log n, and Beep with the rotated list cube root of n into log n. So the minimum you can see is of rotated list. Then insert or delete operation, again Beep is square root of n, and rotated list is square root of n into log n, and Beep with rotated list is cube root of n into log n. And for the extra storage, all the three structures requires the same storage, extra storage, that is log n bits. So this presentation is based on the research paper cited as implicit data structure for fast search and update by authors J. Ian Munro and Hendra Suvanda. Lastly, I want to thank our instructor, Dr. Sudhi Sharma, for his prodigious guidance in this project and course. Thank you.